let's talk about specifically why substituent effects work the ways they do. We mentioned it briefly just before, but activation and deactivation comes from electron density in the ring. If I pull electron density out, let's think of it a little differently in terms of stability of that carbocation intermediate. If I'm pulling electron density out, I'm destabilizing that carbocation intermediate. Okay? I'm making what already is a lack of electron density, I'm making it even less happy. So that's very high energy. Okay? There's a big barrier to get to that, so that's going to be pretty slow. Where if overall I'm donating electron density in, that will stabilize the carbocation intermediate. That'll be lower energy than the other one. It's an easier intermediate to get to. Easier intermediate to reach. Let's just say that. Okay. So activating groups where we're putting electron density into the ring, that makes for faster reaction. So high energy, slow reaction. Easier to intermediate to reach, that's a faster reaction. Okay. The meta-directors are also deactivators. With ortho-para, there's two groups, right? Ortho-para deactivators are halogens, because we said inductive withdrawal outweighs resonance donation. Even though they have lone pairs, they're electronegative enough that they pull electron density out, and they don't really like to donate their lone pairs that much. Ortho-para activators are alkyl groups, which donate inductively, or lone pair containing heteroatoms, where resonance donation outweighs inductive withdrawal. So halogens, the withdrawal wins. Everything else with a lone pair, the donation wins. Let's talk about how that regiochemistry works. Start with ortho-para directing activators. Now, this comes from extra stabilization of that carbocation intermediate if an electrophile adds ortho or para. So let's follow this along and figure out what's happened here. Here I have toluene. We're adding some electrophile to it. In this case, we're nitrating, but this applies equally to any electrophile that adds to something like toluene. So if I add ortho, this is the first resonance structure we would get, just so you can follow it along. Okay, this pair of electrons here would attack, and I'd have a positive charge, which can be translated throughout the ring. Okay? When I do that, when I add my nitro group ortho, here's meta, here's para, what I can end up with is one of these resonance structures where the plus charge is next to the methyl group. Okay? That is a tertiary carbocation where the others were secondary. When I add meta, my plus charge never lands on that tertiary carbon. But when I do para, we do have one resonance structure right there, where the plus charge lands on that tertiary carbocation. So the key to ortho-para directors is that they stabilize. When I add ortho or para, we have one extra stable resonance contributor that lowers the energy of that intermediate and makes the reaction faster. If it's something that's not just a methyl group, if it's something that actually donates resonance electrons in, okay, and I add ortho, we get this extra resonance structure. When I have a plus charge next to an OH group or next to something with lone pairs, those lone pairs can donate in and satisfy that plus charge. It spreads that plus charge up onto the heteroatom, onto the oxygen in this case. So we have that extra stabilizing force, similar to what we had when we had that resonance stabilized carbonyl group, right? The acyl cation. Again, when we do meta attack, that plus charge misses the hydroxy group. We're adding to phenol in this case. But if I add to para, we again have one resonance structure where the plus charge is directly next to that hydroxyl group, where we have this extra resonance structure, where we didn't have before. So the key is, When I add ortho-para to something with lone pairs or something that donates electron in, we get extra stability for the intermediate if I've added in the ortho or para positions. You should be able to draw these resonance structures, and this is not something that you memorize. Okay? Please don't try to memorize what these look like. Okay? Just sort of go one at a time. If I'm doing ortho here, I'm going to take this double bond. I'm going to get plus charges here and here and here. Right? It's always sort of 1, 3, 5 of each other where the charges are. Be able to identify that it's special. When I have a plus charge next to something with a lone pair, that those electrons get donated in. If it's just a plus charge by a alkyl group, that's just a stable, extra stable tertiary carbocation. There's no resonance donation we do, but there is some inductive donation that stabilizes that plus charge. So know those ortho-para directors will stabilize the ortho and para intermediates. Meta has no extra stabilization. There's nothing particularly wrong with it, but it's not nearly as stable as the intermediates we got from ortho or para attack. If I have an ortho-para directing deactivator, like a halogen, it works perfectly the same way. Okay? Regiochemistry is totally the same, where if I have a chlorine, I do ortho attack, I get a plus next to that chlorine. We have that extra resonance stabilization where chlorine's lone pairs can stabilize it. That's why these are still ortho-para directors, even though they're deactivators. This reaction will be slower than reaction of phenol or toluene, like in the last page. Because chlorine is a deactivator, but really the same regiochemistry. We're very similar. If we have an ortho-para director, our product ratio will typically be a mixture of ortho and para positions. And as our original group gets larger, the para position becomes more important. If I have a very small directing group, then it can end up being statistical. So it's a different story altogether when I have a meta-directing deactivator. Okay? Where before we had extra stabilization when we did ortho or para. Here, when we add ortho, for instance, I end up with a plus charge that's directly next to, like, the carbonyl. This is benzaldehyde. There's a partial positive charge on that carbon in the C double bond O. What I have here are two adjacent positive or partial positive charges. Okay? And that's particularly unstable. Adjacent partial positive charges are particularly unfavorable. So we get that same sort of thing when I add para. We end up with one of the resonance structures with that unfavorable adjacent partial positive charges. Okay? And that's bad because we take what was just a positive charge on these other ones and we make it even more positive. Okay? Because it's next to another lack of electron density. So the meta position, there's nothing terribly wrong with it. The ortho and para positions are unstable that way. If I had nitrobenzene, for instance, here, let's draw our nitro group. That's not just a partial positive charge, that's an actual N+. If I were to add an electrophile ortho to it, what I'd end up with would be, among others, here, let's add our electrophile, let's add a hydrogen. Here's N+, O-, double bond O, two double bonds in the ring, same as before, but now I have a plus charge. I have two adjacent positive charges. Okay? The nitro group itself is strongly electron withdrawing, but we're trying to take even more electron density away from that plus charge, making it even less stable. So those extra effects are destabilizing. But do you see the difference here in how ortho and para directors differ from meta directors? In ortho para directors, we stabilize the ortho and para positions. So those are lower in energy. In meta directors, we destabilize those, so they're higher in energy. So the meta position, which is, there's nothing particularly wrong with it, but it's at least not as bad. It's sort of the lesser of two evils, right? Lesser of three evils, I guess we'll think of it that way. So that's going to be important for us to consider in a few minutes when we're talking about whether activating or deactivating groups will win out when we have both of them on a ring. But if I draw just some quick reaction energy diagrams, if I have an ortho-para director, right, something like phenol, the ortho and para positions are stabilized. That's ortho and para. The meta position is not. Okay. Barrier for ortho and para is lower than the barrier for meta addition. So ortho and para will happen faster. If I have something like benzaldehyde, which has a meta director, meta will be about the same energy as meta going on hydroxide, right, on phenol. Okay. Ortho and para are worse. This is why typically ortho-para directors tend to be activators, because that's going to be a fast reaction, and meta directors tend to be deactivators because in general that reaction is slower than this one right here. I always think of it in those terms like that. So let's summarize or work with these directing groups. Activating groups could be alkyl or groups which donate their lone pairs in by resonance. They're both orthopara. The inductive effect for the lone pair donation is not important. Resonance effect is important. Okay? The deactivating groups, like the halogens, they're still orthopara directors because of resonance, but they're deactivators because of their inductive effect. Okay? The meta directors, right, they're deactivators because they have strong withdrawing inductive and strong withdrawing resonance effects. Okay, so that's about it. Let's predict. Should be able to do this pretty quickly. Predict products of reaction of bromine Br2 with FeBr3. So I'm going to add a bromine to each of these compounds. So let's start out with aniline, phenol, and toluene. Those are all orthopara directing activators. So aniline, aromatic group with NH2, Br2, Fe, Br3 as a catalyst. Since it's an orthopara director, I'm going to add my bromine ortho, and as a second product, I can add my bromine para. Let's just draw the products here. Phenol, also ortho-para. So I can do ortho-bromo-phenol, and I can do para-bromo-phenol. Same with toluene. CH3. Ortho-bromo-toluene and para-bromo-toluene. Chlorobenzene, also orthoparadirecting. Although it's a deactivator, the reaction will be slower, right? So, chlorine and bromine, ortho, chlorine and bromine, para. Now we're into the meta directors, so primarily just one product. Okay? All of these will be slow, okay? But benzaldehyde, brominating it, C double bond OH will be meta bromo. Benzoic acid, C double bond OH, meta bromo. Acetophenone, C double bond OCH3, meta bromo. Nitrobenzene, NO2, bromine, meta to it. Okay? So take these, mix them up on a blank piece of paper, be able to identify which ones are orthoparadirectors, which ones are metadirectors, which ones are activating, which ones are deactivating. Okay? Do not do that by memorizing particular groups. That's not going to be helpful to you. So it'll be a waste of your time. Instead, do it by recognizing the common features. Is there a double bond next to the ring? There is in all of these, right? N double bond O minus and that nitro. All these carbonyls have double bonds. Okay? Is it a halogen? Halogens are special, but is there a lone pair next to the ring? In all of these, where there are lone pairs next to the ring, those are all orthoparadirectors. Okay? The halogens tend to also be deactivators, but the alkyl groups are activators, just like the lone pairs would be. So think of it that way.